Welcome back to Pratik Academy. In the last video, we have seen some sample numericals based upon logarithmic decrement. In this video, we'll solve some another examples. Okay. Consider problem statement: a horizontal spring mass system with Coulomb damping has mass of 5 kg attached to spring of stiffness 980 Newton per meter. If mu is equal to 0.025, find out natural frequency. Second one, numbers of cycles required for 50% reduction in amplitude if initial amplitude is 5 centimeter. And last one, time required for this reduction, that means 50% reduction. So here they have given Coulomb damping. So this problem is based upon Coulomb damping. So here given mass is given, K is given, mu is given. So first find out natural frequency. We know that in case of formula for natural frequency is directly under root k upon m. K is given, m is given, so we can directly calculate omega n is equal to 14 radian per second, and it is again frequency of damped vibrations, because in case of Coulomb damping, damped frequency is equal to natural frequency. Now next is a number of cycles required for 50% reduction in amplitude, and initial amplitude is given. We know that in case of Coulomb damping, reduction per cycle is constant and it is equal to 4F upon K, where F is a frictional force and it is given by mu Rn. Okay. As surface here is horizontal, normal direction will be equal to weight, so mu m into g. So m is given, g is a constant, mu is also given, so we can easily calculate this value, and also k is also given, so we can calculate easily reduction in amplitude per cycle, and it is coming 0.5 centimeter. So in each cycle reduction is 0.5 centimeter, but we want 50% reduction of 5 centimeter, that means we want 2.5 centimeter reduction. Okay, so number of cycles required for 50% reduction is total required reduction upon reduction in per cycle. It is 2.5 divided by 0.5, and it is coming 5 cycles. And then next they have asked this time required for this reduction. This time is nothing but time required for completion of 5 cycles. It is equal to 5 into time period of 1 cycle, and time period is nothing but 2 pi upon omega n, and omega n we have already calculated. So putting these values, we get time as a 2.42 seconds. Then next problem is, this is the important problem. Okay. A machine of 75 kg mass is rested on system with 3 springs having 10 Newton per mm stiffness each. There is a fluid dashpot is used as a damper. During vibration, amplitude of cycle changes from 40 mm to 6 mm in 2 cycles. Okay. Number of cycles are 2. Find resistance of dashpot per velocity, and second is a logarithmic decrement. So again here damper is of fluid dashpot, so it is of viscous damping problem. Then 3 springs connected in, okay, system will be look like this: 3 springs and one damper. Here 3 springs are in parallel, so arrangement is parallel arrangement of spring. Then okay, let's start problem. So first is the resistance of dashpot per velocity. We have formula resistive force is equal to, or damping force is equal to C into X dot, because damper is a viscous damper. Then force per velocity, it is resistance per velocity is equal to C, that is damping coefficient. So to find out damping coefficient, we use damping factor formula. Damping factor is equal to C upon Cc, where Cc is 2m omega n. 2 is constant, m is given 75 kg. Omega n can be calculated easily by knowing equivalent stiffness upon mass. As 3 springs are connected in parallel, equivalent stiffness is addition of stiffness of each. So 30 Newton per mm. Putting this value in equation, we get Cc as 3000 Newton second per meter. Now we have find out value of Cc. To get value of C, we use logarithmic decrement equation. So logarithmic decrement is 2 pi zeta under root 1 minus zeta square. So here to find out zeta, initially we have to know what is the value of logarithmic decrement. Now in problem they have given decay in amplitude or change in amplitude 40 mm to 6 mm in 2 cycles. So using another formula for logarithmic decrement, we have 1 upon n into ln of, or log of, x naught upon x naught plus n. Here ln of L is equal to 1 by 2 ln x naught upon x2. So here x naught is given and x naught plus n. Here amplitude after 2 cycles, that is amplitude changes from 40 mm to 6 mm in 2 cycles are given. That means n is here 2. So putting values, x naught is 40 mm, x is 6 mm, and its log ln and its half. So del will be coming 0.9487, and using this value in this equation we can get value of zeta at 0.1492. and now using the value of zeta in this equation we calculated easily C, and C is nothing but damping force or resistive force per unit velocity, and its value is coming 447.80 Newton second per meter. Okay. Next problem is to find out equation of vibration for this system and its frequency. Okay. So system is this: a mass m is attached or supported by dashpot and spring system. Dimensions of various components are given. Stiffness is K. Damping coefficient, let us assume as a C. Distance between spring and support is given B. Dashpot and support is given A, and they are given that all other components is other than mass are of having negligible mass. Now to determine equation, let's assume that system is deflated by small amount theta, okay, in downward direction. Okay. Then accelerating torque is acting in downward direction. It is given by I theta double dot. Then there will be restoring torque developed in system, and the first restoring torque is due to this damper here, force into distance, and second one is in spring location. So when in case of spring it is at a distance B, so this deformation is equal to B into theta, and spring force, due to this deformation, spring force developed will be kb into theta, and as it is at a distance b, so resisting torque will be kb square theta. Okay, in case of damper, it is at a distance a, so its deformation will be a theta dot, and damping force will be c into a theta dot, because damping force is proportional to damping coefficient into velocity. So a theta dot, and it is acting at a distance a, so torque, damping torque or resisting torque will be c a square theta dot. Okay, that is here. Accelerating torque is I theta double dot. Okay, resisting torque is due to first damper and due to spring. Due to damper, force into distance, force is ca theta dot as discussed into distance a, so ca square into theta dot, and due to damping torque due to spring is k b theta damping force, and at a distance b, so k b square theta is a damping torque, sorry, restoring torque due to spring. Okay, now putting these values in equation, we have equation accelerating torque is equal to restoring torque. So accelerating torque is here I theta double dot is equal to restoring torque minus c a square theta dot minus kb square theta. Adjusting term, we get I theta double dot plus c a square theta dot plus kb square theta is equal to 0. Okay, now for I is the mass moment of inertia, and it is equal to ma square, because other components are having negligible mass. So I is equal to m into radius of gyration. Here mass is located at a distance a, so radius of gyration is here a, so m k square is equal to ma square. Now we have got equation in standard form, that is theta double dot plus ca square theta dot upon ma square plus kb square theta upon ma square is equal to 0. Now we know that in case of differential equation for damped systems, the coefficient multiplied to theta or x is nothing but omega n square, it is natural frequency square. So this value will be equal to natural frequency square, so omega n is equal to under root kb square upon ma square. So omega n is equal to kb square upon ma square here. Now we are interested for damped natural frequency. Damped natural frequency, we have find out natural frequency, and we are interested in damped natural frequency. So we have a relation damped natural frequency is equal to under root 1 by 1 minus zeta square into omega n. So putting value of zeta is c upon cc bracket square into omega n. Now again cc can be written as 2m omega n. Okay, now this omega n remain as it is, and taking square we get c square 4m square omega n square. Now if we take this omega n inside bracket, inside this square root, so it becomes omega n square, and again here omega n square get cancelled, so only c upon 4m bracket square. Therefore omega d is equal to omega n under root omega n square minus c square upon 4m square. So damped frequency is equal to under root kb square upon ma square minus c square upon 4m square. So this is equation for damped natural frequency of given system. So in this way we have solved numericals on free damped vibrating systems. From next video we will start our next chapter, that is forced damped systems. Thank you for watching. If you like this video, please share with your friends. Thank you.